Hi, welcome everybody to chapter 16, Current of Electricity. What is an electric current? Electric current is a measure of the rate of flow of electric charge through a conductor. It's given by the formula Q equals to IT. Q is the charge with the units C, coulomb. I is the current with the units amperes. T is the time taken, units seconds. The unit for current is ampere, A, given by the capital A. So before the discovery of electrons, scientists actually believed that electric current was caused by the moving of positive charge. Like I mentioned in the previous chapter, only electrons move. So this idea was supposed to be wrong. So what they believed was the conventional current, which means the positive charge moved from the positive terminal of the battery across the load to the negative terminal of the battery. That is the conventional current. But as we know that electrons move, so electrons move from the negative terminal across the bulb to the positive terminal, and that is called the flow of electrons. Okay, now to draw different circuit diagrams. So the most common components that you need to know of is a cell, a battery, given by these two lines. The longer line is the positive terminal. The bulb, a fixed resistor or a load, a variable resistor, same symbol as the fixed resistor, just with the arrow to show that it's variable. An ammeter, a symbol A, to measure current. A voltmeter with a capital V to measure voltage. This again shows a short circuit when you actually have a wire, across the load or across the bulb. Electrons will flow through the circuit, and when it reaches the bulb, it will actually bypass, which means it will go on the least resistance path, causing a short circuit. Next, what is EMF? Which is electromotive force. Electromotive force is defined as the work done by the source to drive a unit charge around a complete circuit. The formula is given by E, epsilon E equals to work done over charge. The unit for EMF is volt, or you can give it as joules per coulomb. You can see that unit for work done is joules, energy. Charge is coulomb. As a result, epsilon is written as JC inverse, or just simply volt with a capital V. Next, there's two types of arrangement of cells. One is in series arrangement, which means the batteries are placed side by side to each other. Here. Second arrangement is that they are placed opposite to each other, which is called the parallel arrangement. So what is potential difference? PD is the work done to drive a unit charge through a component, such as a bulb, a load, or resistor. The units for PD is the same as your EMF, which is in volts. So what is resistance? Resistance is the ratio of potential difference across the component to the current flowing through the component, given by the formula R equals to V over I. The unit for resistance is ohm. So resistance of a material is actually the property of the material that restricts the movement of electrons in the material. So a higher resistance means you're restricting the flow of electrons. How do you measure resistance? Look on the diagram on the left. You have a ammeter connected in series. And then you have a voltmeter connected in parallel with the component that you would like to measure. It can be a bulb or a load or a resistor. So there's two types of resistance. One is the fixed resistors that has a certain resistance, and another is like a rheostat, which is a variable resistance. For a fixed resistor, the symbol looks like this. For the variable resistor, symbol looks like this with an arrow. These are coils of wire. As I shift this black component up and down, I'm actually increasing the resistance of this rheostat. Next, Ohm's law. Ohm's law states that current passing through a metallic conductor is directly proportional to the potential difference across it, provided that the physical conditions remain constant, such as the temperature of the material, the resistivity of the material. If an object is an ohmic conductor, the IV graph, the current against voltage, will be a straight line that passes through the origin. The formula is also given by R equals to V over I. Ohm's law. For non-ohmic conductor, they do not obey Ohm's law. Okay, so their IV graphs are not straight lines, and which means the ratio is not constant. Two different ones are filament length and a semiconductor diode. You can see that the IV graph are not linear and doesn't pass through the origin. For the tungsten lamp, as you see example above, its resistance changes as the temperature changes. So resistance actually increases as the temperature increases. It's R increases, temperature increases. So it's non-ohmic. Now, coming to resistivity, the resistance of a conductor depends on three things. One is the length. Number two is the cross-sectional area. And number three is the type of material, which is the resistivity rho. So it's given by the formula R equals to rho L over A. R equals to rho L over A. The formula, the symbol for resistor is still Ohm. For resistivity, the symbol is Ohm meter. Length is meter. Area is meter square. So you can see that the meter cancel out meter square remains as resistors is Ohm. Resistivity is independent of the dimension of the material, and it is the intrinsic property of the material. So for example, gold and silver has low resistivity, which means it's better at conducting electricity. So to have a good iPhone charging cable, you will want the length to be, you want resistance to be as low as possible. So you want your resistivity to be low, your length to be short, and your cross-sectional area to be large. Short, so a short and thick wire is better than a long and thin wire. And the material should be made of gold or silver with low resistivity. That's the end of this topic.